Thank you very much for the invitation. So I'll be speaking about how one can might be able to extend differential linear logic with more general differential operators. So basically I'm going to talk a lot about semantics, which is the whole point that justifies what I'm going to tell you. And I'm going to talk a lot about differential linear logic. So I don't think you have heard of differential linear logic yet. It's basically the birth version of linear logic. If you like analysis, then differential linear logic is made for you. So you've all heard now of the Curie-Howard-Lambek correspondence and of its importance in the arising of linear logic. So I guess you've heard that linear logic came from a study of coherent spaces or normal functors. Well, differential linear logic was invented by Thomas Erard and Laurent Régnier after a study of vectorial models of differential linear logic, meaning basically denotational models of linear logic where formulas are interpreted by some vector spaces. And when formulas are interpreted by some vector spaces, well, you can find a way to interpret nonlinear proof as functions who can be differentiated. And because functions can be differentiated, well, why not differentiate proofs, you know? So this is what they did, and I'm going to tell you a bit about that. And then I'm going to tell you a bit about how we can look for a syntax of semantics of differential linear logic with even richer properties and what we can extract from that. Okay, so let's go. Semantics before syntax, I'm going to tell you about the syntax and semantics of differential linear logic. I'm going to talk about topological vector spaces and distribution in a very gentle and naive way, and then I'm going to do just a tad of syntax at the end of the talk. So you might recall that in the canonical, sorry for the typo here, the canonical call by name way to embed to embed intuitionistic logic into linear logic is to say that to a usual implication corresponds a linear implication from bank A to B. In semantics, this translates as to usual, and for me, usual means smooth mean function that can be differentiated. To smooth functions corresponds linear maps from bank A to B. To a smooth map from A to B corresponds a linear map from the interpretation of the exponential from bank A to B. What do we want about, what other features do we want about in the denotational semantics of linear logic? Well, the interpretation of the exponential must be a strong monoidal comonad. It must be a strong monoidal functor, and the strong part here is very specific to differential linear logic, but I'll always be looking for that. So I want something, I want a functor which verifies that bank A tensor B is bank A times B. And the very specific point here is that I really want to interpret the classical part of linear logic. I really want my denotational model to reflect the fact that formula is equivalent to its double linear negation. And what does that mean in semantics? What does that mean in vector spaces in particular? It does mean that a vector space must be reflexive. So I don't know if reflexivity tells you something in mathematics. It does mean that a space is isomorphic to its double dual, the dual of a vector space, just being the space of scalar linear map on that dual. And that's a very important property, and all the fun lies in the fact that it's a property very difficult to obtain once you go to higher order, once you go to beyond finite dimensional vector spaces. Okay, so you've heard a lot about linear logic, but you haven't heard enough about differential linear logic. And differential linear logic has a very, very, very beautiful way of speaking of differentiation in proofs. And it does that by assigning to almost every exponential rule you know, a symmetric rule. Oh my God, and I have a huge typo here in the dereliction rule. If I can I write here? Just to, okay, you are now able to correct the typo that is here, right? Thank you. There is a why not a. So, yes, but I'm not finding chalk. Ah, yes. Okay. So if you just look at the rules as they are here, you can say thank you. If you just look at the rule as they are here, you can see that, well, there is some kind of symmetry about them. So you have contraction, weakening, dereliction, and now you have co-contraction, co-weakening, and co-dereliction. Well, I'm just going to focus on dereliction and co-dereliction, and we are going to leave the two of them aside. Just know that these two rules, co-contraction and co-weakening, are necessary to express cut elimination and to express the global dynamic of differentiation in proofs and in the semantics. Okay, so dereliction is about what? What does dereliction do? Dereliction forgets about the linearity of a map. It transforms a linear map into a nonlinear one, and transforming is merely forgetting about the property that you know that you have about your function. So the interpretation is the same, the type is not. Well, what's the converse of dereliction? The converse of dereliction is making a map linear. And what's making a usual map linear? Well, that's differentiation. And that's the meaning of the co-dereliction rule that you can see here, that I have expressed in another way, but that's basically the idea here. So denotationally speaking, if before you have a proof that it's interpreted by a nonlinear map, you will just have to differentiate this map to find the denotation of your proof. Okay, and that's all. So expressed as before, it gives you this kind of denotation. Okay. So you have the rules, you need to have the dynamic, you need to have the cut elimination one. And the simplest cut elimination rule that you have here is the following one. What does happen when you make a dereliction and a co-dereliction rule interact? Well, this means that what are you going to do? You are going to differentiate a function that's already linear. Well, if you differentiate a function that's already linear, nothing is going to happen. You are just going to land back on the linear function. And the whole point of the talk now is to say, well, what you see here, in fact, is kind of the resolution of a differential equation. I'm going to change here the d0 that you see here to another d. So d0 here represents the differentiation at 0, and I'm going to change the d0 by some differential operator which belongs to a class of partial differential operator for which things works well. Okay, and now I have to go a bit deeper into the denotational semantics of differential linear logic to be able to justify that I have the right here to replace d0 by some other d. I need to find a space where d exists and where I can interpret my proofs and my formulas. Okay, so I'm gonna say basically two things. The first one being the most important one. I'm going to say that exponentials, that's the bank connector of differential linear logic, is in fact a space of distributions. distributions being Schwartz distribution. I'm going to tell just a bit about that. And from distribution theory, we can extract a lot of information that we might be able to get back into our syntax. And I'm also going to say very quickly that reflexivity is something not easy to get, but very fun, that interprets some kind of story about the polarities of your formulas. Okay, so what's a distribution? If you don't know, maybe you've heard that distributions were supposed to be like generalized functions. In fact, for us, distributions are exactly scalar linear maps that act on smooth functions. So a distribution with compact support is something that takes a function and linearly acts on it. So the typical example of a distribution is a Dirac that we see here. It takes a function and it just computes its value at some point. That's typically a good distribution. That's the canonical distribution on which we want to work on. And now let's see quite quickly why the bank connector is exactly a space of distribution with compact support. So you have this syntactic interpretation, this syntactic equality here, which exactly means that two smooth scalar functions must correspond linear function from the exponential to the field of scalar. If you take the dual of these equations, then you get what you have here. And as spaces are supposed to be reflexive, as spaces are supposed to be equivalent to their double dual, then you have like no choice if your functions are smooth. If your spaces are reflexive, then the exponential is interpreted as a space of distribution. So you might try to get your intuitions from what you know about distributions. Sorry, this doesn't work. Okay, another interesting point is that the strong monoidality of the bank that I showed you before exactly corresponds to Seeley's Schwartz kernel theorem. So you might hear of kernel theory as a good way to decompose a distribution which acts on two parameters. It's a very useful tool whenever you do distribution theory or whenever you study partial differential equations. Well, it exactly corresponds to the very useful tool that justifies the name of multiplicative and additive connectives. Okay, so we have a good reason to look for a model where the exponential is indeed interpreted by distributions. Okay, so let's look for something quite general. Let's look for a denotational model of linear logic and differential linear logic where spaces are like general, are like vector spaces, topological vector spaces, norm spaces. And let's look for an interpretation where functions are at least smooth. And in fact, we have two requirements which works as opposite forces. Because you want smooth functions, you want a topology which is fine enough. You want to be able to characterize your topologies. You want a lot of open sets, in fact. But because you are classical, because you want reflexive spaces, well, you don't want too much of open sets, basically. And that's the fun in analysis. We're not in algebra anymore. Everything is messy, everything is unstable, and we have to find the right balance on the topology in order to have both, the best of both worlds, in order to have reflexive spaces and smooth functions. So of course, now I'm going to go a bit quick on that because it's going to be too much semantics. Finite dimensional vector spaces don't work, okay? You need to go towards infinite vector spaces, dimensional vector spaces. The sad thing is that, well, norm spaces don't work either. In fact, it's too much to ask for a norm. Basically, it doesn't work for polarity reasons. So you need to go towards a very general settings, and it's very, very messy. The most important point here being that the duality is not an orthogonality. So maybe you remember from yesterday's talk by Tomaera, he said that, well, duality is interpreted as an orthogonality, what this does means that whenever you don't have an interpretation whenever your space is not reflexive, well, that's okay, you just have to interpret it as its double dual. And its double dual is always going to be reflexive. This works in many denotational models of linear logic. This doesn't work here. So you have to choose the topology that you put on your dual. Depending on that topology, you might not even have a model of multiplicative linear logic. In fact, the simpler the connectives, the messier the semantics. So at the end it works. At the end, you get lucky. At the end, you find this kind of maps of the jungle that lies in topological vector spaces, and you are able to choose a good interpretation from your formula. And we are going to go towards this one here, which are nuclear Fréchet spaces. And nuclear Fréchet spaces are like saying, okay, well, I can't be finite dimensional, that I know. I can't be normed, that I've learned because Girard tried it. But I'm still going to be metrizable. Let's still take a metric on my space, and this is going to work. This is going to work until some point that duality is not going to leave your space. Duality is going to leave your space. The dual of a metrizable space is not metrizable anymore. So in fact, you won't have a denotational model of linear logic as you may have seen, but you will have a model of some kind of polarized linear logic, meaning you have two categories which interact well. One category, one kind of topologies goes with positive connectives, and one other kind of topology goes with negative connectives. If you don't know the names, if you don't know the math, just remember that. In order to have distributions, well, we kind of have two categories that interpret well. And it's kind of very beautiful because there's a lot. There's a topological equivalent for any syntactical construction. Okay, back to syntax. So now I know I have a model, and I can quite safely write that to a proof correspond a smooth function, and to an element of the exponential, the bank connective, corresponds a distribution. So now let's get back in differential linear logic, and let's think about what it means to be linear. How do you characterize a linear map in, let's say, in a very general space, in a space which is not finite dimensional? How would you characterize it? So you can't draw it. You're not two-dimensional. You can say, well, I'm just a line which goes through zero. So in my opinion, the best way to characterize it is to say, well, I'm my own differential at zero. This is what it means to be linear. I am my own differential at zero. So great, it's even a bit stronger because to be linear, it's enough to be the differential of something. If I am the differential of something, then I'm linear. And if I'm linear, then I'm my own differential. So I am the differential of something. Okay, taking the dual of these equations, switching from functions to distribution, what does it mean? It means that I am the composition, I am a distribution which has been composed by differentiation if and only if, in fact, I belong to the double dual of my space. So there is kind of a differential equations between the space A that you see here and the space bank A that you see here. And in fact, here the composition between a distribution and a differential operator is exactly, by definition, the differential operator applied to this distribution. So by definition, in fact, being in the double dual is being the solution of some differential equations. Well, let's go. Then I just have to replace the double dual by some new space. And I have just to replace the differential at 0 by some d. And this constructs a new connector, which I am going to label as bank g. If d is the differential at 0, as in differential linear logic, then I land back on the space I had before. And if d is the identity, then I land back on the whole space of distributions. And in fact, for some very specific class of differential operators, it works well. So I'm not going to detail it. It's just the simplest partial differential operator you can think of, one that can always be solved. Then if it can be solved, then it is a model of some kind of modified differential linear logic whose syntax is here. So I replaced anything that was A before by bank d A. And in fact, in that, I can really model that what direction was about forgetting that the function was linear, and why codirection was about differentiating. Now, dereliction is about solving the differential equations, and codirection is about applying some partial differential operator. Okay, and I won't go deeper into the whole syntax, but just it works. It works. Well, it works with some restrictions, of course. So it works because we don't have higher order. It works because it works from some very specific class of partial differential operators. It doesn't work on ordinary differential equations for which we don't have a canonical way of resolving the equations. So the only insight we have here is that functional analysis and differential linear logic works well together. To logical tools correspond functional analysis principle, and there might be a link, there is a link, which might be small, which might be big, between the logic in linear logic and the resolution of partial differential equations. And that's the end of my talk. Thank you very much.
Daring for questions?
That's okay.
None, I can ask a stupid one.
Okay, so your work seems to be very focused on interpreting classical linear logic because
yes.
You make this relationship with closure.
Yes.
What will be the counterpart of an intuitionistic version of differential linear logic? Does it have a counterpart in the world of analysis?
So, of course, the story goes reverse. I was looking for classical models and I landed on that. But in fact, if the models are not classical, if I don't have reflexivities and I don't have Seeley's isomorphisms, I have like strong monality, but for the why not and then the bang. So I'm not sure how I would even work in these models. And the other thing is like it works because in fact spaces of smooth maps for non-higher order stuff are always reflexive. You just have to find the good categorical setting in which putting them, but the concrete examples we have, the concrete formulas we work on, they are always reflexive. So why leave, you know?
Okay, thanks.